Sklearn pipeline. Description: a scikit-learn pipeline is a powerful tool for streamlining and automating machine learning workflows. It allows you to chain multiple data transformations and machine learning models together, effectively building a complete end-to-end solution. Pipelines ensure consistent data processing, reduce code redundancy, and simplify model management. Inputs: data, the raw data that the pipeline will process. It can be any format that the chosen transformer can handle, typically a pandas data frame or a NumPy array. Target: optional, the target variable for supervised learning tasks, if applicable. This can be a separate column in the input data or a separate array. Outputs: trained model, the pipeline returns a trained machine learning model after fitting it to the data. Predictions: after fitting, the pipeline can be used to generate predictions on new data. Steps: transformers, these are functions that modify the input data, such as scaling, feature engineering, imputation, or dimensionality reduction. Each transformer operates on the data in a sequential manner, with the output of one transformer serving as the input to the next. Estimator: this is the core machine learning model, e.g., linear regression, random forest that learns from the transformed data and makes predictions. Metrics: accuracy evaluates the model's ability to correctly classify instances suitable for classification problems. Precision measures the proportion of correctly predicted positive instances out of all predicted positive instances. Useful when minimizing false positives is crucial. Recall calculates the proportion of correctly predicted positive instances out of all actual positive instances. Important when minimizing false negatives is key. F1 score harmonically averages precision and recall, providing a balanced metric for situations where both are important. Mean squared error MSE quantifies the average squared difference between predicted and actual values, primarily used for regression problems. R squared measures the proportion of variance in the target variable explained by the model. A higher value indicates a better fit. Visualization plots. Confusion matrix visualizes the classification results, displaying the number of correctly and incorrectly classified instances for each class. Useful for analyzing model performance in multi-class problems. ROC curve plots the true positive rate against the false positive rate at different classification thresholds. Helps assess the trade-off between sensitivity and specificity. Precision recall curve shows the relationship between precision and recall at various classification thresholds. Useful for situations where class imbalance exists. Feature importance depicts the relative importance of different features in the models. Predictions. This helps understand which variables contribute most to the model's output. Fine-tune parameters. Hyperparameters of transformers, these control the behavior of individual transformers within a pipeline, e.g., scaling parameters, dimensionality reduction thresholds. Hyperparameters of estimator, these tune the core machine learning model's behavior, e.g., number of trees in a random forest, regularization strength in a linear regression. Uncertainty methods. Confidence intervals provide a range of values around a predicted value, indicating the level of uncertainty associated with the prediction. Prediction probabilities for classification models. These probabilities represent the model's confidence in each class assignment. Bayesian models, models that incorporate uncertainty directly into their predictions, allowing for more nuanced interpretations of results. Challenges and fixes. Challenge 1. Data leakage occurs when information from the target variable unintentionally leaks into the features used for training, leading to overly optimistic performance evaluation. Sample use case that resulted in challenge 1 using a feature that directly depends on the target variable during training. For example, using average price of a house as a feature when trying to predict its individual price. Fixes to challenge 1. Careful feature selection. Ensure that features are independent of the target variable. Avoiding any indirect leakage. Data splitting. Always split the data into training and testing sets before fitting the pipeline. Feature engineering. Create features that are independent of the target variable, removing any potential leakage. Challenge 2. Overfitting. A model learns the training data too well, resulting in poor generalization to unseen data. Sample use case that resulted in challenge 2. A complex model with many parameters trained on a small dataset. Fixes to challenge 2. Regularization. Add penalties to the model's complexity, preventing it from fitting the noise in the training data. Cross-validation. Divide the data into multiple folds. Train on different combinations of folds, and evaluate on the remaining fold. This helps assess the model's generalization performance. Early stopping. Monitor the model's performance on a validation set during training and stop training when performance starts to deteriorate. Challenge 3. Data imbalance occurs when the classes in the target variable are not represented equally. This can lead to biased models that favor the majority class. Sample use case that resulted in challenge 2. A classification task with a large number of instances belonging to one class and only a few instances belonging to other classes. Fixes to challenge 2. Oversampling. Duplicate instances from the minority class to create a more balanced dataset. Undersampling. Remove instances from the majority class to balance the dataset. Weighted sampling. Assign different weights to instances based on their class to compensate for class imbalance during training. Challenge 4. Missing values. Data often contains missing values, which can affect model performance. Sample use case that resulted in challenge 2. A dataset where certain features have missing values, leading to errors during model fitting. Fixes to challenge 2. Imputation. Fill in missing values with reasonable estimates based on the available data. Feature engineering. Create new features that are less prone to missing values. Model selection. Choose a model that is robust to missing values, such as a decision tree or a random forest. sklearn pipeline feature union. Description. Feature union is a transformer in scikit-learn that allows you to combine multiple feature extraction mechanisms into a single pipeline. It essentially takes the output of different transformers and concatenates them into a single feature vector. This is especially useful when you have different types of data that need to be processed differently before being fed into a machine learning model. Inputs. Input 1. The input data can be a pandas data frame or a NumPy array. It can be any data type that the transformers within the feature union can handle. Input 2. Feature union doesn't have a second input. It takes a single input, the dataset, and processes it through multiple transformers. Outputs. Output 1. A transformed feature matrix NumPy array. The shape of the output will depend on the individual transformers used and how they transform pay. Input data. Steps. Step 1. The first step involves defining the transformers you want to use. Each transformer should be a scikit-learn transformer object that can take the input data and transform it into a new representation. You can define multiple transformers within the feature union. Step 2. The second step is to instantiate the feature union object and provide the list of Transformers you defined. Metrics. Metric 1. The metrics used to evaluate the performance of the model after feature union is used are not directly related to feature union itself. Feature union is a pre-processing step. You would evaluate the performance of your model, e.g., using accuracy, precision, recall. F1 score after feature union is used to transform the data. Visualization plots. Visualization plot 1. Visualization plots would be related to the data transformed by feature union. You might use plots like histograms or scatter plots to visualize the distribution of the combined features to understand how feature union impacts the data. Fine-tune parameters. Parameter 1. N jobs. The number of jobs to run in parallel. This can speed up processing by utilizing multiple CPU cores. Parameter 2. Transformer weights allows you to assign weights to the output of each transformer within feature union. This can be useful if you want to give more importance to specific features generated by certain transformers. Uncertainty methods. Uncertainty method 1. Uncertainty methods, like confidence intervals or Bayesian methods, are often applied after a model is trained. While feature union is a pre-processing step, it can impact the uncertainty of the model's predictions by providing a richer feature space. Challenges and fixes. Challenge 1. Overfitting. If the transformers within feature union generate a large number of features, it can lead to overfitting if the model is not regularized properly. Sample use case that resulted in challenge 1. Using transformers like polynomial features or interactions that generate a large number of features without appropriate regularization can lead to overfitting. Fixes to challenge 1. Use regularization techniques like L1 or L2 regularization to penalize complex models. Use cross-validation to find the optimal hyperparameters for regularization. And consider feature selection methods to reduce the number of features generated by feature union. Challenge 2. Dimensionality issues. Combining features from multiple transformers can lead to a high-dimensional feature space, which might cause problems for some machine learning algorithms. Sample use case that resulted in challenge 2. Combining data from text features, e.g., using TF-IDF and numerical features, e.g., using standard scaling can lead to a very high-dimensional feature space. Fixes to challenge 2. Use dimensionality reduction techniques like PCA or TSNE to reduce the dimensionality of the feature space. Select a machine learning algorithm that is robust to high-dimensional data, e.g., random forests. Support vector machines with linear kernels. And consider using feature selection methods to select a smaller subset of informative features. sklearn pipeline. Description. The pipeline class in scikit-learn sklearn provides a way to chain multiple estimators, e.g., transformers and classifiers into a single sequential workflow. This allows you to streamline the process of data preprocessing, feature engineering, and model training, ensuring that these steps are executed in the correct order. Pipelines are particularly beneficial for improving the organization and reproducibility of your machine learning projects. Inputs. Data. The input to a pipeline is typically a dataset, usually represented as a NumPy array or a Pandas data frame, containing features and labels for supervised learning. Estimators. Pipelines are composed of multiple estimators, which can include transformers, feature extractors, and/or models. These estimators are specified as steps within the pipeline. Outputs. Transformed data. If the pipeline includes transformers, the output will be the transformed data after passing through all the transformers. Model: if the pipeline contains a model as the final step, the output will be the trained model. Predictions: if you call the predict method on the pipeline, it will return predictions based on the trained model. Steps: transformers. Transformers are estimators that modify the data, often for feature engineering or data preprocessing. Some common examples include: standard scaler standardizes features to have zero mean and unit variance. One-hot encoder converts categorical features into numerical ones using one-hot encoding. PCA performs dimensionality reduction by projecting the data onto principal components. Estimator model. The final step in a pipeline is typically an estimator, which is a model that learns patterns from the data. Examples include logistic regression, a linear model for binary classification. Decision tree classifier, a tree-based model for classification. Random forest regressor, an ensemble model for regression. Metrics: accuracy for classification problems. This metric represents the proportion of correct predictions. Precision: the ratio of true positives to the sum of true positives and false positives. Recall: the ratio of true positives to the sum of true positives and false negatives. F1 score: the harmonic mean of precision and recall. Mean squared error (MSE) for regression problems. This measures the average squared difference between predicted and actual values. R squared: a measure of how well the model explains the variance in the data. Visualization plots. Confusion matrix for classification problems. A visual representation of true positives, true negatives, false positives, and false negatives. ROC curve plots the true positive rate against the false positive rate for different classification thresholds. Precision recall curve shows the trade-off between precision and recall for different thresholds. Feature importance plots visualize the relative importance of features in a model, helping to understand which features are most influential in making predictions. Fine-tune parameters. Hyperparameters of estimators. The parameters within the estimators used in the pipeline can be adjusted to optimize model performance. Pipeline structure. You can experiment with different combinations of estimators and their order within the pipeline. Uncertainty methods. Confidence intervals for regression problems. Confidence intervals around predicted values can be calculated to provide an estimate of pay. Uncertainty in the prediction. Prediction probabilities for classification models. The probabilities associated with each class prediction can provide an indication of the model's confidence in the prediction. Ensemble methods. Using ensemble techniques like bagging or boosting can reduce the variance in predictions, leading to more robust and reliable results. Challenges and fixes. Challenge 1. Data leakage occurs when information from the testing data is inadvertently used during training, leading to overly optimistic performance estimates. Sample use case. If a feature transformation is applied before a model is split into training and testing sets, it's possible to use information from the test set in the transformation, leading to leakage. Fixes. Fit transformers only on the training data and then apply them to the test data. Use the column transformer to apply different transformations to different subsets of columns. Challenge 2. Pipeline complexity. As the number of steps in a pipeline increases, it can become harder to debug and understand the workflow. Sample use case. Having a complex pipeline with many transformers and models can make it difficult to identify the source of errors or to interpret the results effectively. Fixes. Use smaller, modular pipelines to break down complex tasks into manageable components. Implement logging and monitoring to track the data flow through the pipeline and identify potential issues. sklearn pipeline make pipeline. Description. The make pipeline function in scikit-learn is a convenient way to create a pipeline of machine learning estimators. A pipeline chains multiple estimators together, allowing you to perform a sequence of operations like data preprocessing, feature engineering, and model training in a streamlined and automated manner. Inputs. Estimators. The make pipeline function accepts any number of scikit-learn estimators as input. These estimators can be transformers, e.g., standard scalar, PCA, or models, e.g., logistic regression, decision tree classifier. Outputs. Pipeline object. The make pipeline function returns a pipeline object, which is a scikit-learn estimator itself. This pipeline object represents the entire sequence of transformations and modeling steps you've defined. Steps. Pipeline construction. Make pipeline automatically creates a pipeline object where the steps are defined by the order in which you pass the estimators. Data flow. When you fit the pipeline to data, it sequentially applies each estimator in the pipeline to the input data. The output of each estimator becomes the input for the next one. Metrics. Evaluation metrics. You can use any standard scikit-learn evaluation metrics, e.g., accuracy, precision, recall, F1 score to assess the performance of the pipeline. Visualization plots. Pipeline visualization. Use tools like sklearn, pipeline steps to access the individual estimators in the pipeline and use other visualization techniques to understand the pipeline's structure and behavior. Fine-tune parameters. Hyperparameter tuning. Use grid search, random search, or other hyperparameter tuning techniques to optimize the parameters of the estimators within a pipeline. Uncertainty methods. Confidence intervals. Use methods like bootstrap aggregating bagging to estimate confidence intervals around the predictions made by the pipeline. Challenges and fixes. Challenge 1. Transformer output shape mismatch. If the output shape of a transformer does not match the input shape of the subsequent estimator, an error will occur. Sample use case that resulted in challenge 1. Applying a PCA with n components 2 to data with 5 features, followed by a logistic regression model. Fixes to challenge 1. Adjust the n components of PCA to match the number of features expected by a logistic regression model. Challenge 2. Missing or inconsistent data. If data is missing or inconsistent, pipelines can fail to execute correctly. Sample use case that resulted in challenge 2. Applying a pipeline with a standard scalar to data that has missing values. Fixes to challenge 2. Use data imputation techniques, e.g., mean imputation, to handle missing values before applying the pipeline. sklearn pipeline make union. Description. The make union function in scikit-learn's pipeline module allows you to combine multiple transformer objects into a single transformer. This is particularly useful when you want to apply different transformations to your data before feeding it into a final estimator. Inputs. Input 1. A list of transformer objects. Each transformer object should implement the fit and transform methods, allowing for data modification before being passed to subsequent steps in the pipeline. Input 2. Optional. A list of names for each of the transformers. This is useful for keeping track of the different transformations being applied. Outputs. Output 1. A new transformer object, representing the union of the provided transformers. This composite transformer will apply all the individual transformers in sequence during the fit and transform methods. Output 2. If input names are provided, the make union returns a named transformer. This means the individual transformers can be accessed by their respective names within the pipeline. Steps. Step 1. The fit method of the composite transformer is called. Triggering the fit method of each individual transformer in the list. This allows the individual transformers to learn patterns from the data. Step 2. The transform method of the composite transformer applies each individual transformer in the list to the data sequentially. The resulting output from one transformer is then passed as input to the next transformer. Metrics. Metric 1. None. Make union is a transformer and does not directly compute performance metrics. Performance metrics would be calculated on the final estimator after the transformations are applied. Metric 2. None. Not applicable. Visualization plots. Visualization plot 1. Not applicable. Make union is a transformer. So visualization plots would typically be applied to the final estimator or to the transformed data. Visualization plot 2. Not applicable. Fine-tune parameters. Parameter 1. None. Make union is a function that doesn't have any adjustable parameters. The parameters to fine-tune are associated with the individual transformers within the list. Parameter 2. None. Not applicable. Uncertainty methods. Uncertainty method 1. None. Make union is a transformer and doesn't provide any built-in uncertainty. Quantification methods. You might use uncertainty methods on the final estimator or on the transformed data separately. Uncertainty method 2. None. Not applicable. Challenges and fixes. Challenge 1. The order of transformations can significantly impact the final results. Sample use case that resulted in challenge 1. If you have a pipeline with a standard scaler followed by a PCA, the order matters. Scaling before dimensionality reduction can be beneficial. However, if the order is reversed, the PCA might be applied on data with vastly different scales, leading to poor results. Fixes to challenge 1. Carefully consider the order of transformations and adjust as needed for your specific problem. Challenge 2. Data leakage can occur if the same data is used for fitting and transforming transformers in the list. Sample use case that resulted in challenge 2. If you are fitting a transformer on the entire training dataset and then use the same transformer to transform the training dataset, the transformer might learn about the target variable, leading to data leakage. Fixes to challenge 2. Ensure that each transformer fits on a separate portion of the data. For example, if you want to use a standard scaler on your training data, fit it on the training data only. Then, use this fitted scaler to transform both the training data and the testing data.